Good day, everyone. I'll be taking the second segment of this lecture, which is on structural analysis theorems. Firstly, we are going to look at the principle of superposition. We state that the total displacement of the internal loading at a point in a structure subjected to several external loading can be determined by adding the displacement or internal loading caused by each external load acting separately. What it means is that if an object is being loaded on a beam, as an example, the displacement of that particular object can be read from individual displacement of each loading on that particular beam. So there are requirements that must be followed when using principle of superposition. First is that the material must behave linearly, that is, it must obey the Hooke's law. And secondly, the structural geometry must not change significantly, that is, the small displacement that is only small displacement appear, not that it will deflect and maybe distort out of shape. Now, as we all know, there's what we call the equation of equilibrium, as we already studied earlier on. There are six equations of equilibrium that must be understood when treating an object, which is summation of forces along the x-axis must be equal to 0, summation of forces along the y-axis must be equal to 0, summation of forces along the z-axis, that is when we have our angle s, y, z, our 3D shape, they must follow they must sum up to 0 before you can treat such member. Now, most members that obey this particular law, they are the statically determinate member that we can also treat easily. But however, if we have members that don't obey this law, like the indeterminate members, there are other analysis method that we're going to use to treat their own case. So in that one, we'll be breaking each part into small segments. Then we can now combine the whole members or sum forces together. Let us look at a free body diagram. When we say a free body diagram, for instance, if we have a member that is being, cut in this particular segment, at each point or at each edge, there are activities that take place. We have the shear, the moment, and the axial force that takes place, or the normal force. Now, on the other end of it, the same thing is applicable. However, the only difference is that if the force is acting in this direction in the first instance, then in the other instance or at the other edge, it will be acting at the negative or countering the other force in the other end of the member. As you can see, the moment is pointing upward here, is moving in anti-clockwise direction here, but here it is moving in clockwise direction. Likewise, this one is going is acting downward, while this one is acting upward. So this is an example of shear, how shear takes place. This is an example of moment. Then the sign convention, you must take into consideration sign convention. When I say sign convention, for instance, when you are treating a member, if you are adopting a sign convention that all clockwise forces are positive, you must maintain that sign convention till the end of that particular problem that you are solving. Before you can't just change the sign at the middle of any calculation. Now we have support reaction. Depending on our support reaction, maybe simply supported, roller, pin supported or fixed, the support condition has a lot of things to play. Now, when I say free body diagram, you can see the free body diagram. This is an example of a free body diagram. When I have a member like this, and let me say this is an example of a beam. This is the free body diagram of a beam sample, and we have maybe roller here, and we have pin end here. This is an example of a free body diagram. So I can now put the force here, that I have this force here, and I have just this singular force here. So that's an example of free body diagram. So let me proceed. Let's go to moment area theorem. Moment area theorem. Now it says this theorem was developed by Otto Moore and was later stated by Charles Green. Now the method is advantageous when used to solve deflection problem, that is deflection that involves beam or trusses. Now to develop this theorem, reference is made to beam. Let's take this beam A as an example, that if we draw the moment diagram for this beam and then divide it by the flexural rigidity, that is EI, the M over EI diagram shown, this is the M over EI diagram shown, shows that the theta is equals to M over EI dx. Now let us look at this member. If we have is being loaded this way. Now when we want to draw the bending moment diagram, we have this M over EI. This change, the theta in the slope of the tangent on either side of the element ds is equal to the darker shaded area under the M over EI diagram. This is equals to this, what you are having here. Now if we integrate from point A on the curve to point B, this is an example of if we integrate from point A to point B, then of this M over EI, it will give us our slope. Now the theorem 1 of this moment area diagram is said that the change in slope between 2 points on the plastic and on the elastic curve equals the area under the M over EI diagram between these 2 points. Now the notation theta B over A is referred to the angle of the tangent at B that is measured in radians with respect to the tangent at A. So when we see this sign, you know that it's talking about the angle of the tangent B measured in radians with respect to tangent A. Now, for instance, now we have this is tangent A, tangent B. Now the angle of this rotation measured in relation to this tan A is this what we are talking about here. So you can see it in the diagram. So he said the notation is referred to the angle as the angle of tangent at B measured in radians with respect to the tangent at A. From the proof, it should be evident that this angle is measured counterclockwise from tangent A to tangent B. If the area of the M over EI diagram is positive, see figure 1B and 1C. Conversely, if the area is negative or below the axis, the angle this is measured clockwise. That is, if it's measured this way, it's positive. If it's measured this way, it's negative. Now let us look at this particular diagram here. This is tangent A, this is tangent B. Now let us look at this second. This one is talking about the second moment area. They said the second moment theorem is based on the relative deviation of tangent to the elastic curve shown in figure. Yes, this one. Now, figure 1D is greatly exaggerated. It's exaggeration of the vertical deviation dt of the tangent on each side of the differential elements. So it's let me say different tangents, and it's measured with this let me say in line with this one. You can see this displacement. This tangent is measured, and this are B. We can draw the different tangent like this. So the difference of this is what I'm talking about. Now, he said the deviation is measured along a vertical line passing through point A. Since the slope of the elastic curve and its deflection are assumed to be very small, it is satisfactory to approximate the length of each tangent, line S, and the arc ds by dt. Now, using circular arc formula, we say S equals to theta r, where r is the length of the S. We can write dt equals to S d theta. That is one rotation is equal to M over EI. Now, the vertical deviation of the tangent at A with respect to the tangent at B can be found by integrating in relation to this, just like the way we did the other time. From A to B, S m over ei. Now if you look at this equation very well, it's like it's just like the other one that we have here. The only thing is that we are introducing x to it, just like our normal force the other time when we are calculating shear force. By the time we want to calculate moment, is force times perpendicular distance, which is just introducing s to it. So this one too, when we talk about slope and displacement, they're just almost the same thing. The only difference is that we are multiplying with the distance s, which is why it's changing. Now the second moment area theorem can be stated as the vertical deviation of the tangent at a point A to the elastic curve with respect to the tangent extended from another point B equals the moment of area under the m over ei between the 2 points. This moment is calculated about point A, where the deviation t of A or B is determined. Now it's just but one thing I want us to know is that in this second moment theorem, if we have this tangent here, we have this tangent here. Now this tan A, this tan B. The displacement from here to here is the t of A over B, while the displacement from here to here is t of B over A. However, this t of B over A is different from t of A over B. So that's the main difference about these two. You can see that they are different. So the procedure for moment area method using this is that we first determine the support reaction and we draw the moment m over ei diagram. If the loading consists of a series of concentrated load or coupled moments and distributed load, it may be simpler to calculate the required m over ei area and their moments by drawing the m over ei diagram in parts. They will now use method of superposition as discussed earlier. Now the second procedure is that we draw an exaggerated view of the beam elastic curve. The displacement and slope to be determined should be indicated on the curve. Now, since the moment area theorem applied only between two tangents, attention should be given to as to which tangent should be constructed so that the angle of deviation between them will lead to the solution of the problem. To do this, the tangents at the point of known slope and displacement and those at the supports should be considered, since the beam usually has zero displacement and or zero slope at the support. Note this is very important. This area usually has zero displacement and or zero slope at the support. Now the moment area theorem, apply to theorem 1 to determine the angle between two tangents and theorem 2 to determine the vertical deviation between these two tangents. And after applying either theorem 1 and theorem 2, the algebraic sum or sign of the answer can be verified from the angle of deviation as indicated on the elastic curve. Now let us look at this example so that which will be more clearer to us. Let's say for instance that we have a cantilever beam in this sort. This particular cantilever beam is having two different members joined together. You can see that this one is having I of 8 times 10 raised to the power of 6, and this one is having I of 4 times 10 raised to the power of 6, and it's 1 meter, while this one is 2 meters span. Now we said determine the displacement at points B and C of the beam shown here. Now values for the moment of inertia of each segment are indicated in the figure. Likewise, we are taking E to be equal to 200 gigapascal. Now let us look at if we have this object. I said the first thing is that we draw the m over ei diagram, which is the moment diagram. To draw this particular moment diagram for this, because even though this is a cantilever, but because there's a moment applied here, we must have that moment, we must put that moment there. However, the other moment for this particular point is just 250 over ei. Now if we after drawing our m over ei diagram, the next thing we will do is that we consider our elastic curve. First thing you do is that you are asked to determine the displacement at point B and C of the beam. So you must note your question, what you are being answered, what you are being asked. displacement at point B and at C. Is displacement here and here. So what we're going to do is that we draw the target at the 2 points where we are asked to calculate displacement, and then we draw this taking reference to point A. We measure our tan and our displacement from each other one. Now for this particular one, you can see the displacement. For this one, you can see the displacement here. Now the couple moment at C causes the beam to deflect as shown here. The tangent at A, that is the support, B and C are indicated. We are required to find theta B and theta C. This displacement can be related directly to this deviation between the tangents, so that from the construction, theta B is equal to the deviation of tan B relative to tan A. That is, theta B is equal to this over into B relative to A. Displacement at B relative to A. Now likewise, this one will be the same as displacement at C relative to point A. Now applying the moments and theorem 2, which says that this displacement is equal to the moment of the area under the M over EI diagram between A and B, calculated about point B. Since this is the point where the vertical deviation is to be determined, hence we do our calculation from the initial distance. I told us the other time that the only difference is that from this particular illustration, I told us the other time that the difference is that we are multiplying x with this. So now likewise, this is what we are going to do. What we are going to do is that we are treating B with respect to A. Now what's the distance of that B with respect to A? Is just 2 here, which is what we are going to consider here. This the moment is this M over EI, which is 250 over EI. We place it here. Then the distance of this one is 2 meters. This AB is 2 meters, which we put there. Now times 1 meter will give us this particular one. Now the second thing we are going to do is, sorry,